This is camphor. It's a white solid and it gives a good pungent smell that is used for treating cold and congestion, right? Like in Vicks. The inhaler has the major ingredient camphor, right? Okay, but in today's lab, we're going to use this camphor to synthesize isoborneol through a reduction reaction. We're going to reduce this functional group ketone into an alcohol functional group, right? How do you do that? We need to put a hydrogen on the oxygen and hydrogen on the carbon and remove this pi bond to get an alcohol, right? Okay, so we basically need two hydrogen sources. One of the hydrogens should be an H minus. The one that goes to the carbon is H minus, and then the one that goes to oxygen is H plus. So you need two types of proton sources. Two types of hydrogen sources, H minus and H plus. The first hydrogen source is sodium borohydride, which has the hydrogen nucleophile. You might have used this in the alcohols chapter to synthesize alcohol through reduction reaction. This is exactly the same reaction that you studied in the alcohols and phenols chapter. Okay, so hydride is a good nucleophile, but it does not exist simply as hydride. We need to find the parent compound, that is borohydride. Borohydride, BH4, which is BH4, like this, with a negative charge on boron. The formal charge on boron is negative, so we need a counter ion, that is sodium borohydride. That is the name of this compound. And if you look at this borohydride, the sigma bonds are polarized towards hydrogen. That is unusual to have a hydrogen with a partial negative charge. In most cases, like in alcohol, NH, CH, in most of the cases, the other atom, these atoms are the electronegative atom, more electronegative atoms, right, compared to hydrogen. But in this case, boron is less electronegative, which makes it the electron to go towards the hydrogen. So the bond breaks like this. Hydrogen takes the two electrons. It's a good leaving group in this case, right? You can also use aluminum hydride, which is even stronger reducing agent, lithium aluminum hydride, right? Stronger reducing agent. Boron and aluminum are like this in the periodic table. In the same column, they behave similar. But aluminum hydride is stronger reducing agent because the length of this bond is longer compared to the borohydride, right? So it's a longer bond, so the electrons can go with the hydrogen easily. We'll study more about this in the lecture, but for now, hydride comes from borohydride. Okay, so let's simply write H minus, and the H minus will attack this sp2 carbon. The geometry of the sp2 carbon, you all know that it's trigonal planar. Right? So it's a plane. The nucleophile hydride can come from the top of the plane or from the bottom of the plane. There are two types of attack. They're both possible. So you get two possible products. they are isomers to each other, right? So let's draw two arrows like this, one from the top. Technically it should go like this from the top, and maybe we'll draw this way. And the other one is from the bottom. Right. So which one is more favorable, the top attack or the bottom attack? It looks like the bottom is more favorable, because when the hydrogen approaches from the top, it has to pass through these hydrogens, right? The steady, which can cause some steady hindrance, right? So this is less favored compared to the bottom attack, less favorable. And this CH3 on here, it's not on the way, it's pointing in a different direction. It is not on the way of the hydride, so there is no steady hindrance. The product of these two types of attack, top and bottom, would give two products. Right? Here is the O minus and H. Right? So when you attack the carbon, this pi bond will break and go to the oxygen to give O minus. Oh, I think this is the bottom attack. So let me move this to here. Right? Hydrogen coming from the bottom. Hydride. Now here is the hydrogen coming from the top, and the oxide ends up in the bottom. After this, you'd use water, H2O, in a separate step, or you can also use methanol, CH3OH. Basically, you just need a mild acid, this hydrogen, or the hydrogen in the water, or the mild acid, right? Okay, so either one can protonate. To get the final product. OH, alcohol. Right. So this hydrogen is coming into the compound as a proton. Let me use green color for that. Right, it's a proton from the acid that is here on the oxygen, right? On the oxygen. The other one came from borohydride as hydride. So two types of protons, so two types of hydrogens, H minus and H plus. Okay, the one on the top is called borneol, right? It is also a compound that gives a pungent smell and used as a medicine for cold and topical cream. Okay, and this is isoborneol. And we just discussed that the bottom attack is more favorable, and it gives isoborneol as the major product. Right? These two are isomers, stereoisomers, and the major one is isoborneol with a hydrogen in the bottom. Right? We'll do two techniques to identify the completion of the product and the amount of borneol and isoborneol. To check the completion of the product, we'll use IR spectroscopy, infrared spectroscopy. Right. The IR spectroscopy of Camphor, which has the ketone functional group, right? The IR spectroscopy of that would give a strong peak at 1700, around 1700 centimeter inverse 1. That is for the C double bond O, and there may be some 3100. Sorry. 2900 peak, that is for the sp3ch. Right. After the reaction, when this is turned into either isoborneol or borneol, the functional group is now alcohol. All of the ketone are gone, and you have an alcohol. Right. So we are looking for a peak like this at 3500. It could be stronger than this, and the 2900 for the sp3ch. This is for hydroxide in the alcohol, and the 1700 peak should be disappeared. You shouldn't see anything at 1700, right? No peak. The C double bond O is completely gone. This marks the completion of the reaction, appearance of hydroxide peak and disappearance of the ketone peak. In your IR spectroscopy, let me check. In your IR spectroscopy, some of you cannot see the hydroxide peak. I tried several times. I couldn't see the hydroxide peak in the IR spectroscopy. You may see a tiny, a small dip like this, but not much. I couldn't figure out why. It could be the hydroxide is deprotonated. It could be deprotonated and there is no hydroxide. There is no hydrogen on the oxygen. It is one possible reason why you couldn't see a strong hydroxide peak. Right. But you should not see this peak. That is important in your IR spectroscopy. There shouldn't be no 1700 peak. Okay. That tells the completion of the product. Now the NMR spectroscopy. In the NMR spectroscopy, you are looking for the proton, that is this proton, you're looking for this proton in the NMR spectroscopy. Oops. Yeah, these two protons in the NMR spectroscopy. Right, they will, for the isoborneol, the hydrogen is on the bottom, and the borneol, where the hydrogen is on the top, they end up at a different chemical shift in the NMR spectroscopy. Right, the isoborneol should be close to, I think, 3.5 or 3.6 ppm, right? 3.6 ppm. And look at the splitting pattern of this hydrogen. You have two hydrogens here, and there is no hydrogen on this carbon. There is no hydrogen on this carbon, and there is a hydrogen on the oxygen. Right. The splitting pattern could be probably a triplet or a quartet. And if this hydrogen is not on the oxygen, like we said in the previous page, if that hydrogen is not on there, you'll see a triplet. Right? Okay. So a triplet for that hydrogen. And this is not a pure product. It is a mixture of isoborneol and borneol. Okay, so we have two hydrogens here, and see a triplet for this, and that triplet is here for isoborneol. For borneol, you probably see something like this, close to 4.0 ppm. It's because they're close to this red hydrogen is spatially close to these hydrogens, right, on the methyl group. So they have some different chemical environment, and it ends up in a different location in the x-axis of NMR spectroscopy. Now, how do you know how much isoborneol and how much borneol are there in your mixture? You can measure the size of the peak, and you can look at the size of the peak, the volume of the peak. Sorry, did I say volume? The area of the peak, right? The area of these two peaks. We call it integration, right? Look at the area, and the computer can calculate the area and give it in the bottom, like here. It could be 3 or 4, and this one could be 1, which means you have a 3:1 ratio of isoborneol to borneol, right? That is how you measure the amount of two stereoisomers in your compound. Okay, so there's one more question on the post lab. Why did you use a solvent for the IR spectroscopy? The IR spectroscopy works like this. You have a sample platform. You put the sample on this platform, and the IR spectrum, the IR light will, I think the IR light comes from this side. Here's the IR light source. It comes from this side. If it's a solid, if your compound is a solid, it may not have a good contact with the IR. We need to make a something like this on the platform. So the IR, which is actually, the IR is behind the platform, and it's passing like this, right, through the platform, the sample plate, right? If it's a solid, it may not have a good contact with the light, but if it's a liquid, perfectly dissolved in a solvent that is not IR active, dichloromethane. Dichloromethane is this, right? 2 chlorines on methane. Dichloromethane does not have any alcohol group or ketone group, so it does not interfere with your sample. Right? Don't use acetone. Right? Acetone has a ketone functional group. This is acetone, right, that we use in our lab as a solvent to wash our glassware. This has a ketone, right? This may give a false peak, false 1700 peak. So don't use acetone, but use a dichloromethane solvent. Okay, that's it.